What's going on, smart people? Bringing you another Tensor Calculus for Physics video today. You know, in the last video we talked about some frequently encountered two-index tensors in undergraduate physics, and we learned how to do things like express them as square matrices. But one thing to keep in mind is that not all matrices are tensors. They have to exhibit certain transformation properties. And that leads us into the goal of today's video. Today we're going to talk about transformations of two-index tensors. But before we go into transforming tensors between different frames, let's learn how to develop a picture of tensors in a coordinate-free way. And to do this, let's pick on the inertia tensor. So we remember from last time that we can talk about the components of the inertia tensor if you're projecting it onto some x, y, z coordinate system as the following. We can say the ijth component of the inertia tensor is equal to the integral of, we have the Kronecker delta, ij, r squared minus xi, xj, integrating all these little chunks of mass. Okay, but there's another way that we can represent this. Now, if we were to take the inner product between two basis vectors of some quantity that we're calling the inertia tensor, that would look an awful lot like this, right? In fact, it would be the exact same. So one thing, some bookkeeping that we can establish is that the I basis dotted into our inertia tensor and the j basis is the exact same thing as the ijth component here. It's equal to ij. Okay, now let's try to establish some Dirac notation with what's going on in this integral as well. Well, delta ij, that's the same thing as just the dot product of two orthonormal basis vectors. Right? If I doesn't equal j, then this is then it's 0, and then, yeah, great. And then the same thing goes with r squared. So r squared is just equal to the inner product between r and r. And we can assume that r is going to be Hermitian, right? It's all good, it's all real here. And then we can do the same thing with this I here. So xi, that's the same thing as the I basis dotted with r. And again, because it's all Hermitian, that means that we can also write this as Ri. Awesome. Now, let's put all this stuff inside of this integral. And when we do that, we get that Ij is equal to the integral of, I'm going to write r first, r, and then we got delta ij minus xi, which is here. So we've got ir. And then this is the, I'll show you why I wanted to write it this way right now. So we have, this can be represented as rj dn. Okay. Now, in order to be able to talk about the tensor itself, what I want to be able to do is you can think of it as factoring out these two basis vectors. Okay, so if we want to do that here, what we get is that this becomes, whoops, ij is equal to, make this I. I'm just going to write it out and then I'll explain what's going on here as soon as I'm done. Minus. Okay. So basically all we did here was, since we're not integrating I or j or anything like that, we can think of it as pulling it outside of the integral. So we got an I out here, a j out here. So we're factoring out those bases from whatever this matrix is, or whatever this matrix element is, which is going to give us the unit matrix. And then the same thing goes on here, and all we have is the outer product between r with r. And what we see is that we have an I outside here, j outside here, I outside here, j outside here. So by looking at this, that's telling us that this quantity right here we can define as the inertia tensor. And this means that we can sandwich this definition of the inertia tensor between any pair of unit basis vectors to give this kind of relationship. Now I think we're ready to start tackling transformations of these two index tensors. And in order to do that, we're going to revisit something that we did when we were talking about vectors as matrices. And then it's going to go back to change of basis. So we can define some vector A in terms of its components. We have the coefficients and then the basis vector where we're summing over I. And then we can take some other basis vector, and we're going to use the completeness relation as a jumping off point, so we know that the unit matrix is equal to the outer product between this other basis vector. Oops, there we go. And what I'm going to do is I'm going to take the inner product with alpha and A. So it's going to give me the alphath component of A. Okay, so alpha A is equal to some weird quantity alpha I AI. And in that video, in that vector video, what we showed is that this quantity here, this inner product that's going on here, is our transformation coefficient. This was our dx prime alpha dxi. And we also came up with a name for this thing. We defined this to be some quantity that we named alpha or lambda alpha I. And this is what we're going to need for the next part of this video. So if you're not comfortable with this logic here, go revisit the very end of that video that I just discussed, and that should clear things up. Okay, next I'm going to leave these relationships here. We just have the completeness relation and we have this transformation coefficient just for reference. And what I want to do is I want to take the components of a tensor and we're going to learn how it transforms into a different reference frame. So if we take, say, the alpha beta component of some tensor I, and what I want to do is I want to stick in the unit matrix inside of here. So it's not really doing anything. So we have alpha, the unit matrix, I, unit matrix again, beta. Okay. So next what I'm going to do is I'm going to substitute in our definition of the completeness relationship here where we have our basis vectors. And I'm not going to repeat the same basis vector because that won't be too useful. So this is going to be equal to alpha, and then this is this. So we've got I, this tensor here, and then let's call it J for this one. J, beta. Okay, great. Well now, here, this looks familiar, doesn't it? Right here, this is just our transformation coefficient. So this reduces to alpha, or lambda, I always call it alpha, I, and this is just going to be the ijth component of the inertia, or the I tensor, ij, and we can flip this. Well, let's keep it like this. Actually, this is going to be jb, and due to the Hermitianness of this matrix, we can also express this as alpha I, ij. Let's put a little parentheses in here. And this is just for preference of how to format this. bj. There we go. You know what? Let me say that again. In order to swap the rows with the columns, we have to take the Hermitian conjugate, which is the complex conjugate transpose. And we want to do that just so that we can get it in this form. So that's why we're writing it in this way. And this looks a little bit weird, but effectively what this is doing, what these coefficients are doing, is it's giving us a map, or it's giving us a guide on how to map the coordinates in this reference frame to the coordinates in this reference frame. Continuing this logic, what this tells us at the end of the day is that if we transform into some frame, some primed frame, that can be written as the transformation matrix times the tensor untransformed, and then we have the Hermitian conjugate of the transformation matrix. And next what we're going to do is, well, this contains the information of how the tensor's components transform, and that's what's next. So that contains the information for how the components of the two-index tensors transform, which we can explicitly write out just by using basic rules of matrix multiplication. So if we say we want to transform into some alpha beta prime reference frame, well, that's going to be equal to, we know it's going to be proportional to our transformation coefficients, the original unprimed reference frame. So let's call that one ij, and then the dagger one. Okay, so if we want this to be transforming into alpha beta, then we can make these indices alpha I, and these ones will be j beta. And this is going to be j beta, not beta j, just because we're doing the Hermitian conjugate, remember that. And then we can take a look up here where we defined our transformation coefficients in terms of the partial derivatives, and we can explicitly write out that this is equal to dx prime alpha dxi, and then we have the ij, dx prime beta dx j. Make that a little bit cleaner, and this should look very familiar. Dx prime alpha dxi dx prime beta dxj ij. And there we have the definition of a tensor by how its components transform. And this was the main goal of today's video, but so for the rest of this video, we're going to be focusing on verifying this through an example. So we're going to be taking the inertia tensor as an example and seeing that it has these transformation properties. So let's go ahead and write out the components of the inertia tensor, assuming we're projecting it onto some xyz coordinate system, in which case we have iij is equal to the integral, we got r squared delta ij minus xi xj dm. And then let's say, we can still be in an xy coordinate system, but a slightly different one. Okay, in which case we can be transforming into some, I prime, j prime, which is equal to r squared delta I prime j prime minus xi prime xj prime dm. And the way that we're going to be transforming, we'll use the orthogonal transformation that we established earlier, in which case, if you don't remember, we have x prime is equal to x cosine theta plus y sine theta. Y prime is equal to minus x sine theta plus y cosine theta, and z prime is equal to z, because we're rotating about the z-axis. Okay, so let's consider the case where we're interested in the xy component of the inertia tensor, and we're transforming into the x prime y prime component. So explicitly what I mean is I xy, what is that equal to? Well, this is going to be pretty straightforward, right? Because this component is going to go to 0 because I does not equal j. So this just becomes minus the integral of x times y dm. And we're transforming into the I x prime y prime, which is equal to minus the integral of of x prime y prime. And what we can do here is substitute in this transformation rule. So this is equal to minus the integral of x cos theta plus y sine theta times minus x sine theta plus y cosine theta dm. And the next step is to just FOIL this out, which I'm going to do right now. Cool, that was easy. Now let's take a look at this here. We have an integral of x squared, integral of y squared times this stuff. I'm going to take some freedom real quick to fix our z-axis. I'm going to fix our z at 0. And I'm going to do this because we're going to have this constant following us around that's eventually going to get differentiated out anyways, and I'd rather not have to write it, and it's not consequential to this. So for the rest of this, z equals 0, that makes z prime equal to 0. Okay. And I think it'll be clear why I want to do this in just a second. So let's take a look at this. In order to make sense out of this, we're going to need to consider different components of this tensor. For example, let's take a look at the y component of this tensor. That's going to be equal to, well, delta y, that's going to be 1 r squared. But what is r squared? It's normally x squared plus y squared plus z squared. But, awesome. So r in this case is equal to x squared plus y squared. Okay? And if we substitute that in, we get x squared plus y squared minus y squared. So this part cancels, and we have a dm. So we get Iyy is equal to the integral of x squared dm. And that's basically this part right here. Integral of x squared dm times this cosine sine business. And if we do the same thing for Iyy, or xx, sorry, I know that this is getting a little bit busy, I'll erase it in a second. That's going to be equal to, following this logic, it's going to be equal to the integral of y squared dm. So that tells us that we can rewrite this thing as, it's going to be Iyy minus Ixx times the cosine of theta sine theta. And then the same thing goes with this one. You can substitute xy into this and follow the same logic and see that this is going to give us a minus Ixy times sine squared theta minus cosine squared theta. Great. So now we've expressed the xy component of the inertia tensor in terms of other components of the inertia tensor scaled to some degrees. And there's going to be something to do with these scaling factors. That's the next topic that we're getting into. Okay, so I've rewritten what we did down here up here. So we have our xy prime components of this tensor in terms of these components. And now we want to find out, is this consistent with this transformation rule? And in order to find that out, we're just going to expand the transformation rule. So according to this, if we expand this out in our case, we have I prime xy is equal to, so it's going to be dx prime, start with dx, dy prime, dx, I xx, and then let's go to y now, so plus dx prime, dy prime, dx, dy, I xy, and then now let's switch to the y part here, so plus dx prime, dy, dy prime, dx, I yx, plus dx prime, dy, dy prime, dy, I y. Okay, so this is how this transformation rule says that xy transforms into this, or how this tensor transforms into this frame. So now the next step is to calculate these coefficients based off of this transformation rule. So the next scene I will have all of these derivatives calculated, and then we can work on plugging these in here. Awesome. Here are the transformation coefficients. I calculated them just by taking derivatives of this with respect to these variables. So dx prime dx gave us just this cosine theta, and so on. Now what we're going to do is we're going to be substituting in these coefficients into this long expression here, into this long equation here. So for example, this dx prime dx is actually just a cosine theta. So let's go ahead and do this. So that tells us that this is equal to, we have a cosine theta, dy prime dx is a minus sine theta, so this is totally, or in total, it's going to be a minus cosine theta sine theta I xx, that's our first term. And then we have dx prime dx, which is still cosine theta, dy prime dy, which is going to be a cosine theta, so this is plus a cosine squared theta I xy. Then moving over here, dx prime dy, which is going to give us a sine theta, dy prime dx, which is going to give us a minus sine theta, so it's minus sine squared theta I y x. Last one, dx prime dy prime dy, which is going to give us a plus cosine theta sine theta I y y. Let me just check that one more time. Dx prime dy prime dy. Yeah, that looks good. And the first thing that pops up when comparing this to this is, hey Andrew, this one has xy and yx. What gives? This one just has the xy. Well, take a look at the definition of the components of this tensor, right? If you switch I with j, does anything change? Well, we know the Kronecker delta is symmetric, right? Because it's just a square matrix of 1 and zeros, a diagonal matrix actually. And then if you take a dot product between these basis vectors, or between these vectors, or if you multiply really just x with y versus y with x, does that make any difference? No, not at all. So that tells you that the inertia tensor is a symmetric tensor, which means, if I haven't talked about it before, that Ij is equal to Iji. Okay, so that means that's why we have two expressions for xy here. One of them is secretly the other if you flip the row in the column. Okay, so if we just do a little, need to really combine this all. Let's just take a look. So we have Ixx has a minus cosine theta sine theta, that works. We have Ixy having a cosine squared theta, so we have a minus sign here, that works. And then we have a minus sine squared theta xy, that works. We have the minus with the sine squared. And then here we have cosine theta sine theta Iyy. Perfect, beautiful. And that's exactly why I decided to make the z 0, because when we take the derivatives it would go away anyways, and that just sounded like one more way to miss the point. But at the end of the day, what we showed is that it does agree with this transformation rule, so this is a valid way of expressing how components of tensors transform. And one thing to take away from it, let's think about how scalars transform. Well, they transform as the same thing, right? If we have some lambda prime equal to lambda. And then we can also talk about some vectors. Some vector v I prime, let's say prime, is equal to dx prime I dxj, and then let's just call this vj. So we have a way of expressing how vectors transform in terms of the partial derivatives, and now we also have how tensors transform in terms of partial derivatives. And one thing to notice is that as the number of indices increases, as does the number of partial derivatives, these transformation coefficients increases as well. And so this is why you can sometimes call a scalar a tensor of rank 0, a vector of rank 1, it has one index, a 2-index tensor of rank 2, and so on. And just like that, we've reached the goal of this video. In the next video, what I plan on doing is, well, some of these tensors will have off-diagonal components. Now, is that because the system that you're working with is intrinsically complicated, or is it a choice of your reference frame, or what is it? So in the next video, I'm going to show you how to try to diagonalize tensors, how to get rid of those off-diagonal components, and we're also going to show an alternative way of expressing how these 2-index tensors transform, which I think might paint a little bit more of an intuitive picture than this did. So I want you guys to chew on this, watch this video, see if it makes sense to you. If it doesn't, I'm going to provide a slightly different angle at tackling this in the next video. I hope you guys found this helpful and a little bit useful. Let me know in the comment section if you did, and I'll see you guys there.